Hey everybody, welcome to a new video of Amazing Mac Stuff. So this is actually the first video of a new series about particle system. So I know that I already made some tutorials about particle system, but this was really the first one, which is kind of the most famous tutorial of mine. It's really already pretty old, and the others as well. So Max actually moved quite forward in those times and introduced some new ways to create particle system, more efficient ways. And also, in this series, we're going to go through the creation of a particle system in a structured way. So we will really start from scratch and then build up on that. So we are really starting with the basics. We are starting with the basic physics, actually, in this episode. And then we're going to move on in the next episode. And in the end, we will arrive to move the calculation from the CPU. So from jit.gen, we will move the calculation to GGLTF, so to shaders. So we're using the transform feedback system, and we are going to see how we can efficiently move our particles in the world and how we can actually render them in cool ways. So this is going to be as well on the physics side of the particle systems and also on the rendering side. So we're going to see how we can render those particles then in the end in order for them to be really good looking. So particles were created in the beginning of the computer graphics world to simulate stuff that you could not model as a single object. For example, water, fire, fireworks, snow, rain, all things that are composed of tiny little particles that you can actually not model as a single object, right? So this is why particle systems were created. So a particle is actually a tiny little object. Let's say you have a tiny little set of pixels on our screen that is moved around by certain logics, by certain rules. So mostly it's the rule of physics, and sometimes it's some other arbitrary rules. We can really use whatever we want. And we are going to be able to move particles using vectors. So in jit.gen and in GLSL we can use vectors. This is very convenient because these allow us to work with vector mathematics and apply kind of the rules of physics to our three-dimensional world. Okay? So in this first video we're going to use only, let's delete the GGLTF, we're not going to use this one. We're going to use the jit.gen and the GGL mesh, and we are going to see really from scratch how we can move our particles in the world. For what concerns us at this point, a particle is simply a vertex of the GGL mesh object rendered as a point. So let me actually create a JIT world, so we will have our three-dimensional world in place. I will call it, without much imagination, I will call it particles, so JIT world particles. I will give it the floating one, attribute size 320 by 240, FSAA, full scale anti-aliasing, erase color, let's erase like a kind of a grayish color. And I think this is going to be it for the moment. So have I created another one? Okay. So let's create a toggle to actually activate this world. You can actually have it enabled by default. So enable one, and there it is. Okay, cool. Now we have to set the GGL mesh particles draw mode. So draw mode is going to be draw mode point. Now, in the latest update of the GL3 package, we got something interesting for the GGL mesh, which is the possibility to draw our points as actually little circles. So if you go into point mode, here is a new attribute for GGL mesh that the great Rob gave us. And we can actually choose now if we want to render our points as a circle using depth, square using depth, square not using depth, and circles not using depth, or define the behavior from a user shader, which is a super cool possibility. So we're going to explore all this stuff in the future. For the moment, we are really good by drawing our particles as circle points, okay, as is the default. So we are going to work basically with a position array, so the vertex array of the GGL mesh. Now remember, GGL mesh only accepts a matrix as an input, okay? Unless we are working with a GGLTF system, in all the other cases, GGL mesh only accepts matrices as input, okay? Even if it's a GL object, so works on the GPU, it only wants data from the CPU as an input. So we're going to work with jit.gen for the moment. Now, before we connect this to jit.gen, we can make just a little test and use a jit noise with 3 planes, float 32 and 100, to simply generate 100 dots in our screen. So if I bang on this and I activate the jit world, and nothing happens because I actually wrote this wrong. It's actually points, not point. And this doesn't seem to be the problem. So color. Oh yeah, there we go. There they are, our little particles. So let's make them actually bigger. So let's give it a point size of 3, for example, so we can actually see them. And there they are. So this is 100 particles, let's say, of vertices. Basically, they are vertices of our GGL mesh object represented as points. So we see them actually represented as circles in our 2-dimensional world. Now, why have I choose 3 planes for the jit noise? Because every plane coming out from the jit noise matrix is going to contain a coordinate for an axis of those particles in the world. For example, the first plane, the plane 0, is going to contain the x coordinate for those particles. So if I would have only one plane, this would only be x coordinates. As you can see, it only became just a line that goes from 0 to 1, because jit noise creates numbers in the order in the range 0 to 1, random numbers between 0 and 1. So it only gave us values for the x-axis of those particles. If I would have 2 planes, we will fill the x and the y axis with particles, because we will have an x and a y coordinate. So let me write this down. Plane 1 is the y coordinate. Then plane 2, as you probably guessed, is going to be the zeta coordinate. Okay. So this is why we're using 3 planes, because we want to work in 3 dimensions, and in 3 dimensions we need to use 3 planes, because every plane contains a single coordinate. So basically, our matrix that comes out from the jit noise is going to be a 1-dimensional matrix in this case, with some cells inside. These are our cells, and every one of those cells includes 3 planes, right? So it's going to have inside an x coordinate, an y coordinate, and a zeta coordinate in the order of numbers. So these are going to be just numbers. For the moment they are between 0 and 1, so for example it could be 0.2, then 0.3, and then 0.4, something like that, right? Now, what we are actually creating here is already a vector. So every one of those cells contains actually a vector with 3 components inside. So what is actually a vector? A vector is simply a collection of numbers, let's say. But why do we need vectors then? Why we cannot just work with arrays or call it like collection of number? The thing is that vectors, to be defined as vectors, they need to have a direction and a magnitude, which is their length. So how actually long they are. I explained this as well in the previous tutorial in the jit.gen 0 to Hero series. I will put the link in the description for that one. But let's just review it. So vectors have a direction and a magnitude. If I just say a number 5, for example, and I represent this as a distance, so from 0 to 5, this is not going to be a vector, because it's just a distance. Even if this would be a movement, I don't have any clue on what is its direction. So if I move from 0 to 5, this is actually in, let's say, 10 seconds, this is actually speed. Speed is not a vector. Velocity is a vector, because if I would have like 5 and then 0 for the y, then I actually know that this is a vector that is parallel to the ground, that is going in the direction from left to right. So how do I know that this is going from left to right? Because the vector here, this is always going to be considered the head of the vector. So this is always going to be considered the point of arrival of the vector. Okay, so if this vector arrives to 5 and 0, where does it start? Well, if it's not specified, so if I don't define the tail, so this is going to be the head, if I don't specify a tail, it means that our tail is going to be the vector 0, 0. Because if we don't specify a tail, it's always going to be considered the origin, okay? So if I would like to find a vector that goes from point A to point B, and this is inside our Cartesian system, for example, Cartesian coordinate system, if I would like to find this vector, I just have to subtract the tail, this is the head, I have to subtract the tail from the head. So basically what I want to do is going to be head minus tail. Okay, so for example, if this vector has components 5 and 5, let's say, and this has components, let's say 1 and 2, so 1 for the x and 2 for the y, then I have to do 5 minus 1 and 5 minus 2, and this is going to be my new vector that goes from here to here. Okay, so this is going to be 4 and 3. So this vector has components 4 on the x-axis and 3 on the y-axis, okay? These are the components of my vector. And it doesn't really matter if this vector is here, or is in whatever other position in our Cartesian space. What it really matters is its length and its direction, okay? So maybe a bit confusing for the moment, but this is going to be very useful in the future. So last thing, why if I have no components I always consider the tail to be 0, 0, because if I subtract the head from the tail 0, 0, I simply remain with the head, which is going to be our vector. Okay, so we basically just consider the tail to be the component 0, 0, because this doesn't affect the components of the vector. Okay. So we will better understand this stuff surely in future videos. So as soon as we start to do stuff in practice, we'll definitely understand these things better. So let's actually delete this JIT noise. Let's connect the jit.gen to our GGL mesh. Let's create, let's actually just connect this metro that we receive here from the middle of the JIT world, not actually to our jit.gen object, but simply to a JIT matrix. Let's call it JIT432. Let's start with 100 particles, right? So we connect this here. Okay, so now, inside the jit.gen, so this matrix is filled with 0, and we are just passing this matrix on the output, so basically we are having all the particles are all focused here on the center. Let me actually create a GGL camera, so we can move around in the world. Let's call it particles, look at 0, 0, 0, actually look 1 and tripod 1 so it doesn't tilt. And let's then create a jit.anim drive, jit.anim, to move around. I stopped the scheduler, something very annoying because I never remember how to actually make it start again. Okay, so I found out how to restart the scheduler. So we can go on. So basically we want to have here UI listen 1 and speed, let's say 20, something like that. And then let's give the message anim reset, both to the camera and the anim drive object. Okay, cool. So we can now, hopefully we can now move around in our world. Okay, but we cannot see it yet because we just have got a little particle in the center. So, okay, so what we want to do now, if for example, let's start with those particles in a line. So we want simply to have a line of particles that is simply here, as we did before with the noise, we just want a line of particles. But this, the x-coordinate of those particles is not going to be chosen randomly, but I'm going to choose this from the S-norm object. Now, if you don't know much about the objects inside jit.gen, I made a video series about jit.gen, which is still going actually, in which I describe most of the objects you can find inside jit.gen and how to use them. So if you don't know what S-norm is, for example, I will put the link in the description for the tutorial. But I encourage you to watch the whole series because it's going to make things much easier when you want to create a particle system. So let's actually switch, we don't even need to switch the x coordinate, because this matrix has just one dimension, which means the S-norm object is just to create coordinates for one dimension, so it's already a single number. It's not a vector inside this S-norm. It's if every cell just has a single number. So we're using here a vector because we basically are setting the position of those particles using a vector. So in this case, this is not really representing a direction, this is called a position vector. So a position vector is simply a vector that it doesn't really represent a direction, represents just a position. So it's basically just a point in space in the form of vector. And this is going to be very useful for us in the future when we are going to move this position vector. So, okay, as you can see, we created a row of particles that go from -1 to 1, because the S-norm object creates coordinates between -1 and 1, right? And we're using only the x, we're using these numbers to set the x coordinate. Okay, very well. So now we got our little row of particles. Now let's say that I want to make our particles fall, right? I want to make them fall. So what do I do? In order to make them fall, I want to sum to the position of those particles another vector that points toward the bottom of the screen, right? So this is my particle. I want that this particle from position, let's say 0, 0, 0, goes down to position, let's say -0.10. Okay? So what I want to do is to create a vector that goes exactamente in this direction. So how can I do that? Simply by creating a vector, setting a x coordinate of 0, an y coordinate of -0.1, for example, and a z coordinate of 0. So why only the y? Because I'm moving only on the y axis. If I will get also a coordinate x, then this will move diagonal, right? If I will have, for example, 0.1x minus 0.1 y, this will move diagonally, which I don't want. I just want to go straight down. So what we can do, what we have to do now, is to sum those two vectors. Because if you sum a vector, like let's say this is our position vector, if you sum the vector that goes like this, we basically get this vector plus this other vector, so we get a new position vector that is basically down here, right? Pretty basic. So what we want to do is to sum those two vectors. And as you can see, the particles move down of 0.1. Okay, but that's it. That's it, because at every frame, the particles are going to be reset, their position is going to be reset to some x coordinate and 0 and 0, and then it's going to be summed to this vector, which brings them down one little step. But this is not making them fall, right? So to make them fall, what we need to do is to basically save this position at the beginning. Put this position inside another matrix, which we're going to call position, and we're giving a name to this matrix. Then I'm going to copy the same matrix and putting this on the output of this jit.gen, because we will see in a second why. So I don't want to connect these anymore here. I want to connect these actually to the position. And before I actually go there, I want to create another jit.gen to basically initialize our position here. So I don't want to have any vector here, any addition of vectors here. I just want to initialize the position of our particles, okay? So if we simply connect this here and bang this matrix here, this is going to be our initial position, right? Now, here, inside our second jit.gen, I don't want to use anymore, I don't want to initialize the position anymore. I actually want to use the position from our input. And as you saw, these little particles just fell down. So let's restart. And there you go. They are basically falling really fast. So in order to make them fall slower, we actually have to make this number smaller. Because then, exactly, there you go. Now they are falling really small. Let's maybe actually make it a bit faster. Okay, cool. So what's going on here? Let's review the passages we just done. So here, let's call this gen let's actually give it a title, and let's call it position initialization, so init. I see some people just writing position init without writing title. That's actually will give you a warning, because it's not an argument. You cannot use as an argument. This is going to be the attribute title. Okay, if you want to give a title to your jit.gen, you have to use the title attribute. Just a little thing. Okay, let's actually delete this input too, because we don't need it. So, okay, cool. So once we initialized our position, the position is going to go inside the position matrix, which will take the same characteristic of this matrix here. So this will have 3 planes, float 32, and 100 cells. Okay, you can check this from the attributes of this matrix. Okay. Now, why this matrix has a name? Now, the thing with matrices with a name is that the content of one matrix that has a certain name is going to be copied to a matrix that has the same name. It's actually not going to be copied, it's just that the matrix refers to the same space in the memory of the computer. Okay? So that's why, if I simply fill this matrix with, for example, a bunch of random numbers, let's make it 2-dimensional. If I simply fill this matrix with some random values, and then I bang this other matrix, I actually access the same values that are inside this matrix, because they refer to the same place in memory. Okay? So this is what happens. The initial position goes inside this matrix. Then it goes inside the jit.gen. So this then gets banged from the jit world, goes inside the jit.gen, gets summed to this vector, and goes in the output in a matrix that is called as this matrix. So now the content of both those matrices became the content of the position plus this vector. Now, when this matrix gets banged again, it doesn't have anymore the initial position as the new position from the previous frame, okay? So basically, it made a feedback from this matrix to that matrix. So this matrix gets worked again, the new values gets transferred to this new matrix, to this other matrix down below, and now the values inside those two matrices are the same. So in the next frame, when this gets banged, this gets worked again, and then this goes inside the jit matrix position and creates a feedback loop, basically. So if, for example, our vector in the beginning was, let's say, 0.2, 0, 0, and it gets summed to the vector 0, minus 0.0010, 0. This is frame 0, let's say. In frame 1, the matrix will contain not anymore this vector, but we contain the vector 0.2, minus 0.001, and 0. And then it gets summed again for the same vector. Probably you'll see where I'm going. And then in the frame 2, this is going to be vector 0.2, minus 0.002 this time, 0. And this is just the position in our world, right? So this basically means that every frame the position is going to get lower and lower. So that's why those particles are moving. Cool. Now I hope this is clear enough. If you got some questions, just let me know. We are going to review those logic in the next video. But for the moment, I really hope this is clear enough, and I really hope this was kind of helpful. This is our little first step in the world of particle system, and we are going to see in the next videos how we can evolve on that, and we can build on that, and we can make it cooler and super fancy particle system. Just before we go, we can just do one thing. We can wrap, for example, those positions between -1 and 1. So once it arrives at the bottom, it will just start up back on the beginning, right? Because we are wrapping every coordinate, so also the x and the z as well, we are wrapping them between -1 and 1. So when this goes below -1, you start back from 1, just wrapped the numbers. So thank you very much for following, and if you want to support me, you can check my Patreon, where I share a lot of patches that I don't share in public, and you can join also the Discord community. So, thank you very much, and see you soon with the next video. Ciao ciao!